Good morning or good afternoon, wherever you may be. My name is Madelyn, and for my final presentation for Galois Theory, Math 172, I will be giving a very brief introduction to the p-adic numbers. Since this presentation is quite short, we will give a few preliminary definitions that are necessary to understand the definition of the p-adic numbers, and then I will talk about one related theorem and one application of the related theorem. Now, a little bit of a spoiler, that related theorem will be talking about Fermat's last theorem. If you're familiar with Fermat's last theorem, we will get there and we'll talk about how it is related because the statement of Fermat's theorem doesn't quite seem to be related at first glance. Now, before we may give the definition of the p-adic numbers, we must first address, as I mentioned, some preliminary definitions. First, what is a valuation? So the definition here talks about what a discrete valuation is. But a valuation, instead of going to the integers, just goes to a totally ordered abelian group. So we're going to talk about a discrete valuation because it uses a set that we are more familiar with. So if we have a field k, a discrete valuation is a function from k to the integers plus infinity that essentially assigns an integer value to each element of the field. And it must satisfy the following properties. For two elements, x and y, in our field k, any two elements, our discrete valuation must satisfy the following. The valuation of x times y is the valuation of x plus the valuation of y. The valuation of x plus y, at least the valuation of x and the valuation of y. And finally, the valuation of x is infinity if and only if x is equal to 0. Now, this is related because we care about the p-adic valuation, which is a type of valuation that we will use to define the p-adic numbers. So if we are given a p-adic integer x, we will define the p-adic valuation to be the assignment that assigns x to the largest integer n, where p to the n divides x. So how does this really work? Well, we may represent any non-zero rational number x uniquely as p to the a times r over s, where p is a prime. We have integers r and s that have greatest common divisor of 1, and p does not divide r or s. We will then denote the p-adic valuation of x as p to the negative a. Now we can go back and verify this is the valuation, but we will not do so as this is a very short presentation. Now, we also need to talk about what a completion is. However, we did see this notation in class with the inverse limit notation, and so I have not included it in this presentation as it is in the class notes from 2 weeks ago. But essentially, if we have a field k, the completion of our field k with respect to a valuation functions in the same sort of way as the completion of a metric space with respect to a metric. And in fact, the p-adic numbers are the completion of the rational numbers with respect to the p-adic valuation x minus y of p. Now note that this is written in the metric notation, which we should recall from taking analysis and learning about metric spaces. And so this sort of puts it in the same framework as the completion with respect to a metric. Now this may seem like an unfamiliar definition. We did see a definition of the p-adic numbers in class very briefly 2 weeks ago, and this is actually the same definition. However, when we say the completion with respect to the valuation, those are words in place of putting the actual inverse limit notation as we did in the class notes. So they are the same definition. In essence, p-adic numbers allow for us to encode congruency of rational numbers with respect to a prime of our choice. Now, rather than consider major theorems about p-adic numbers, I've decided to touch on a famous theorem that was proved using p-adic numbers. So let's talk about Fermat's last theorem. Now, Fermat's last theorem from around 1637 states the following. For any integer n greater or equal to 2, no 3 positive integers a, b, and c will satisfy the equation a to the n plus b to the n equals c to the n. At the time, Fermat claimed that he had a proof that was too long to fit in the margins, and so he didn't include it when he published this theorem. However, mathematicians had their doubts. Considering the fact that it took 300 years for the first actual proof to be published, and it used techniques that were not available at the time to Fermat, Fermat's last theorem was called Fermat's last conjecture for a while because people didn't believe that he had actually proved it. The jury is still out on that. So the theorem was first proved successfully by Andrew Wiles in 1995 using p-adic integers. Now, the proof for this was 129 pages long, so I will not even begin to summarize the details of the proof. If you'd like to read it, it's online, a great thing to do over winter break. He uses p-adic integers in the first proof of Fermat's last theorem by attaching the p-adic representation to an elliptic curve. Again, the details are all in the proof online, it's very long. And so this is a use of p-adic numbers in a famous proof. And an example of this theorem is that if we say n equals 2, there are no positive integers a, b, and c, such that a squared plus b squared equals c squared. However, if n equals 1, the theorem does not apply. And so we can very easily find 1 to the 1 plus 2 to the 1 equals 3 to the 1. Now, in general, p-adic numbers are very helpful in solving Diophantine equations, which some of you may be familiar with from number theory. Remember that they allow us to encode congruency with respect to primes, and that allows us to kind of make our Diophantine equations a little bit more simple to work with. Now, that is all we have time with for today. Thank you for listening.